I am on a hill in Galway. It is really, really windy. I brought my chart, the little chart. Wanted to bring the big chart, but it's too windy. I'm a computer guy, I'll figure it out. So what is a graph? When we say graph, what we mean is a set of vertices, or nodes as we call them in this project, connected by edges, which is the lines in between them. In this one we have A, B, and C. So we want to color the graph. That's the graph coloring problem, right? So in this example you can see how you have a different color assigned to each node. That's called a feasible coloring, but it's not an optimal one, because in this case B is not connected to C. That means that B and C could have the same color. If two nodes that are connected do have the same color, that means they're in conflict. So, how do we color the graph then? Well, most of the time there's a centralized approach. This is usually something like the greedy algorithm, where you start with node A, you assign it a color, you move on, then you keep assigning colors as you go along. However, the problem with this, it is so windy. The problem with this is that if the problem changes, you have to start again. What we want is to mostly map these problems to real-world problems. You have changing resources, changing topology of the graph, the problem that you're mapping. That's what distributed graph coloring is all about. Instead of having a centralized knowledge of the graph, we give each node the responsibility to color itself based on its surroundings. In this example, B knows it's connected to A, but it knows absolutely nothing about C or that it even exists. Although A technically has complete knowledge of the graph, it actually doesn't know what nodes are in it. For all it knows, D, E, F, and G could be connected to B as well. Decentralized approaches give us the advantage of being able to adapt the problem to whatever happens or whatever we need to do. So how are we going to represent this? Well, we can create a struct which stores the critical information about each node, and then we can put it together into a list. This is better than things like adjacency matrices or adjacency lists. One is a giant matrix of mostly redundant data where we say, yes, this node is connected to that node. But if we want to add nodes or remove nodes, it's a massive operation. No good. The other alternative is an adjacency list. This is more a mathematical way, but it's really difficult to find information in it, especially for large graphs. You can spend ages searching. So I came up with an in-between, a node list. For our node list, what we're going to do is we're going to put these nodes into a list, G. Grand. The problem with this is we're going to be moving this information around a lot, and if we want to keep track of each node and what they're connected to, we don't want to be copying an entire 24 bytes all over the place. Instead, what we can do is abstract this to another level. Instead of saying, here's our list and it's full of structs, we're going to say, here's our list and it's full of pointers to structs. Now, A, B, and C are pointers to their actual struct representations in memory. What's great about this is we can then abstract it to another level. We can say, alright, A now has a second list of node pointers, which points to its neighbors, B and C. From this, we can see how we can get from B to C without actually needing to have complete knowledge of the graph. It's a completely decentralized solution.
Alright, so now that we've had that high-level overview of the memory, we're going to have a look at what it actually looks like. So I'm going to zoom out a bit here. We're going to jump over to the node struct. So this is what it actually looks like. So we have our node type. Each node stores an ID, a color value, which is stored as an integer, and the degree of the node. Then we have a recursive neighbor list, and that's it. Like, that's all we need to store. Compared to an adjacency list and an adjacency matrix, like I mentioned, it's actually pretty efficient, and it's much more useful for what we're going to do, as you'll see in a bit. So next up is how we actually make use of this. So in order to show that, I'm going to jump over to the coloring kernels. And these are the functions that actually define the behavior of nodes. So I talked about how in a decentralized problem, each node works by itself. So we want some way to, define this behavior in a kind of reasonable and understandable way. And this is that way. So we have our minimum agent here, for example, is our definition of the minimum local color algorithm, essentially. So previously we jumped from a kind of naive approach, which is slightly better than random, where we color the graph, but we don't know what agent is or what node neighbor is causing the conflict, or what color they have, or anything. So it's a naive approach. We don't know anything. Versus in minimum local color, each agent can retrieve the colors in its locality and apply the one that is to itself, that is minimal. So it literally just minimizes the number of colors in the graph, and it's kind of self-optimizing as well. And you know, if you look at the report, which can be found in the GitHub, you're going to see that the results are pretty good for this algorithm. So we have our agents and we have our kernels, which we can plug into the agents to define their behavior. And we do this for both the coloring process, but we also do it for some others. So we need a way to combine it all together into a overview of a decentralized problem, which we can kind of control. So this is done here. So it might look like a complicated function, but essentially this is the line that matters. It isn't here that we return the number of changes, and this is essentially our convergence mechanism. So if you return 1 or 2 or whatever, that's the number of changes that the kernel made to the graph. So this is a kind of way to collect the information, but not provide it to the graph. It's all kind of abstracted away. So here we have our dynamic kernel. So this is what we use in order to make changes to the actual topology of the graph while we're coloring it. I do this in a separate loop since it's just not advisable to, you know, you apply the coloring and then you apply a dynamic thing to change the list, but we're not trying to update values in the list at the same time. Just to slightly remove an aspect of complexity there. Although there's nothing stopping you from kind of combining this, as we'll kind of talk about later. So in the dynamic kernel, you'll kind of see that we're using a lot of pointers to different things. And this is for a very particular reason. So I talked before about how we have our node pointer, which is a list of node pointers to structs which store the data that we need. So this allows us to kind of use different functions for either the whole graph or localities or anything like this. When we're making changes to the dynamic kernel, you can see in GraphUtil, if I scroll down, if we want to remove a node, we pass a node pointer. So this is a 3-star programmer moment. But the reason we do this is because it's just simpler than creating an entire copy of the graph and then returning it and updating it. It's essentially the same result, but in 2 different ways. And we'll see in a minute how this actually really benefits us when it comes to actually coding in the kernel. So this is a perfect example. So this could be used so this is used in the minimum agent to find the the colors that are in the locality, but it could also be used on the whole graph because it's the same exact thing. You just give num nodes, this is the degree if it's the locality, or it's the number of nodes if it's the whole graph. You have this kind of very adaptable API and structure which can be kind of used on any part of the graph. But when we're changing the topology, it's just more straightforward to give the function a reference to our graph. So we're just passing a reference to the actual list of node pointers. So that's what's going on here. So although it looks complicated at this point, when we actually then use this in the dynamic kernels, it abstracts away all this complicated logic. And essentially what we're left with is all we have to do is define a condition and then remove and remove. And that's it. So although we have all these references and everything, the API design abstracts it all away as it kind of generally should. This is in stark contrast to something like the coloring kernels where the inputs are immutable. And this is, generally good programming practice where you have your inputs and you don't change them and then you produce an output. The problem with that is we're writing it in C. So I need to update the graph reference, the number of nodes, the number of agents, and the list of agents. Like, all of these things need to be updated from this function. So it's not practical or reasonable to just input, parameters and then output one thing at a time. Like, especially when we're running things like this, it abstracts away all this complexity. Before we get on to the demo, I'm going to talk a little bit about the way we test the code. So the tests are compiled in, I'll show you here. So we have our source, which is actually relatively small, but this is all called from this main function here, where we have all of our inputs and parameters, and it kind of sorts through and then calls the main program loop. The problem is, how do we test this? So in order to do this, I created basically a testing framework. We compile the code with a filter out in the makefile, which allows us to kind of replace the main function with our main function, which just loops over a whole load of unit tests. So then I can test the util functions by just inputting the logic and return 0 if it passes, or return 1 if something is wrong. And the advantage of this is I wrote it over 2 different machines. One is running Windows, one is running Linux. So a lot of this kind of thing was caught, like, the free graph function, it was working properly, but this lets us test the actual logic. So it's provable, kind of like, okay, this does exactly what we want it to do, and we're happy. So the only overhead is that because it's in C, we have this test list where we essentially add, create this structure where we have the function and the name of the test, so that it's just easier to loop over them all. So we can run this by just make compile test, and that will produce this executable over here, test coloring. So test coloring, and here we go. So everything is passed. Fantastic. All right. So that is it for the code demonstration. I will now move on to actual experiments. Okay, so now that we've gone over the structure of the code, the way this node is stored, the way it's tested, the way it kind of fits us together, now we're going to go over some examples. So in the GitHub repository, there's an example usage section, which gives a whole lot of different commands that you can run. It demonstrates the way you can kind of dynamically put things together. So the first one we're going to do is color a ring graph. So we're going to use -go, and it's going to have 51 nodes, 51, and we're going to limit the number of iterations to 10,000. And basically this means, because we iterate over each generation in the evolutionary process, we want to not go on forever, but the default is 50,000 in this program. So we want to say, no, just leave it 10,000. If it can't do it, can't do it, but it will in this case. So a ring graph is just a graph where each node has degree 2, and it's kind of in a ring formation. If this has an even number of nodes, it'll be colored with 2 colors. If it has an odd, it'll be 3. So there we go. We have our number of colors, 3. And our degrees are 2 and 2. All right, next up, we have coloring a random graph, which has a probability of 30% that each edge exists. So the command for this is the most default that we can probably do it. And the reason for this is because most of the experiments in the project are run on the Erdos-Rainey model, which is essentially just a mathematical model for producing random graphs, where you have a node and each potential edge that the node has connecting to every other node in the graph has a percentage chance that it exists. So we can use the generator explicitly with -g or, but we don't need to do that. So instead we can just use its probability option and say 30% chance. And I'm going to bump this up to 100 nodes as well. So here we have our roughly, you know, average 30 neighbors for each node, and we have whatever, it just colors the graph. You can also just bump this up to whatever you want, like 0.8, and then we have, you know, roughly 80. Or you can go as high as 1, and that's where we have a fully connected graph. So in 100, every node will have a degree of 99, and we will need 100 colors to color the graph. In the next example, we are going to be doing a fully connected graph with 1001 nodes, but we're going to be doing a slightly different thing. So we have our setup of 1001 nodes, fully connected, and now we want to limit it to using at least 5 colors, but at most 50. And basically the reason for this is so that we can kind of test different algorithms and see what their tolerance is for colors. So obviously 1001 nodes, we're going to need 1001 colors. But what if we want to color it with just 50 colors? You know, there are real world problems where you have a certain limit on the number of resources that you have, and you need to find a way to distribute them properly. So how good are these different algorithms at distributing the resources? So we can see here it's going to think for a bit, and then it'll just run for 145 iterations and realize that all it can do is apply 49 colors and then kind of give up. So we have 952 nodes which didn't get a color applied to them. And that's just because of the algorithm. So I can change the algorithm by saying -k, and then I'm going to use a naive random approach. So we're going to see how long it's going to run for. It's probably going to be quite a while, so I'm going to limit it to 10,000 iterations. And there we go. So 100,000 conflicts, but it used only 5 colors. So it this doesn't increase until there's kind of no changes for a certain amount of time. But because the random kernel will just check, is there a conflict? All right, I'll change my color. It's going to constantly change. So we're just going to run forever. So you see up here we have ran for 145 iterations. We don't see that here because it just hit the limit. Now we're going to do another more complicated experiment. And in this experiment, we're using a kind of weird idea of having, you know, okay, so we have our whatever graph of 0.7 density, but then, you know, generally we'll have 300 agents in this setup. So I can run it here and it'll say, oh, there you go, you have 75 colors. That's not a particularly good result though. So we have 69 colors there, fantastic. But it just runs for whatever, and we have our 300 agents. So what if instead we wanted to reduce the number of agents? So I can say -a, and I can say I only want 50 agents in this experiment, but I also want them to move each time. So this -m will define that on each iteration, they're going to move somewhere. So in order to do this, we need to have our -w option in order to define our optimal move algorithm, which is essentially just an algorithm which will check if the agent has an uncolored neighbor and go there. Otherwise, it'll pick the quote-unquote least optimal neighbor, which is the one with the highest color, and see if it can optimize it. We're also going to repeat the experiment, and we're going to do it 3 times. So let's see what we get. So compared to the benchmark, you'll notice now it's much more difficult for the algorithm to actually color the graph but it still manages to reach, so we have no missed nodes and no conflicts, because it still managed to find a feasible coloring by moving around. Interestingly, if you use 2 colors, you're going to end up with this kind of 1, 1, 2 kind of pattern, and the colorings are much worse, but the times and the number of iterations are much faster. So the reason for this is essentially that if you think about like a line of 3 nodes connected, then you can kind of see how an agent which can only move twice will just get stuck. It'll just be able to go over and back, and it won't be able to actually reach certain nodes. So that's what's happening here. So the last example I'm going to go over is using a random graph and a configuration option to kind of use a dynamic experiment. And this experiment, we're going to have 100 nodes, and we're going to say it's roughly half connected. And then we're going to say -k, capital K, and we're going to define that we're going to use the decrementing kernel, the node removal kernel. So this is a dynamic kernel which removes a node with a certain probability. And then we don't want a mobility kernel, so we're just going to leave it blank. We're also going to view the graph afterwards, and we can do this with -v. So you'll see now in a second. So number of nodes now, 95. So it removed 5 nodes from the graph based on a certain probability. So we're also now in this traversal mode, which is where we can see this little diagram of the graph, and we're starting at 92, which is the highest degree node. This traversal mode, we have our little set of commands here, so I can say, we can just go next and see what's there. So each node kind of displays a color in the terminal capacity just as much as it can, but I can just like jump to a certain node, and then I can say, I don't want node 0 to be connected to node 3, so I can just C3, and now it's not connected. And then I can just say OR, and we can see if we made any updates. No, so that didn't let us improve the coloring at all. And then I can just exit it like that. So that's a general kind of demonstration of how the program can actually be used in a practical sense, what it can do, the different experiments you can run. So yeah. All right, so we've had a background to the project, we've gone over the code, we've done a demo of the existing project. The last thing we need to do is expand it and see what else we can do in a really short amount of time. The reason we're doing this is because part of the goal of this project was to create a tool which is easily expandable for this kind of like niche area of research of like dynamic graphs and adapting the graph coloring problem to real world situations. So all of the kernels have really defined function signatures, the structure of the node struct being kind of recursive and allowing you to use utility functions on the whole graph or just the locality. All this kind of thing makes it super easy to adapt the program to your needs. Basically, all you need to do is add a kernel, add an option which lets you use it from the command line, and you're set. So the one we're going to be doing is a tag kernel. Basically, the graph is going to play tag, but it's with a particular goal. So what we want to do is see, so we know the highest degree node at the start, so we're going to print out what node that is rather than just what degree it is. And then we're going to see if the distributed system is able to find it as well. So first things first, we're going to jump over to the main function, zoom out a bit for sure. And we're going to take this part here, which is the highest degree. We can just cut this out and say we'll get the node, we'll just call it highest is equal to this. There we go. And then we're going to say highest degree, and we're going to also print out the highest and its ID. I'll do comma %d. Cool. So this will print out the degree and the ID of the node with the highest degree, so we're able to verify that we're actually getting the right answer when we do it. So step one is we're going to change the node struct to have a new field. And this is just going to be a Boolean value, so integer, and it's just going to be called chosen. And this will let us check if this is the node which is currently tagged, basically. So in order to make use of this, we have to jump over to graph_util, go right up to the top, and in the initialize graph function, we need to add graph chosen is equal to 0. That's graph n as well to you. Okay. Cool. So now we can get right on to creating an actual kernel. So we can go into the coloring kernels, and right at the bottom here we can say int tag kernel, we can just call it tag kernel, and we're going to follow the function signature. So we pass in an agent and the max color, which we don't need for this, but we have to color it, or have to follow the function signature anyway. So for this kernel, we're going to introduce a bit of centralized knowledge for initialization's sake. So we're going to say initial tag made, and we're going to say that's 0, because we just initialize every node to have chosen equal to 0. We then need some mechanism. So for this, we're just going to say if initial tag made is not made, and there's some random chance, it's like a 1 in 100 maybe is fine. So if that's the case for this, then we're just going to say that agent chosen is 1. We're going to say that the initial tag has been made, and we're going to return 1 because change has been made to the graph. So now that that's done, we need to define the behavior for if this is not the tagged node, because this node is basically not able to do anything. And because we're not really using this as a coloring experiment, this is an experiment on the ability of the distributed system in order to achieve some goal, we can just return 0. And that's all we need to do, because nothing will be done. So then we can do the actual definition of the behavior of the agent. So the first thing we need to do is get the next node, which is the find node with highest degree, and agent neighbors, and agent degree. And you can note how this is the exact same function that we were using in the main function in order to identify the highest degree node in the graph. So this is an example of how the API is designed and the whole structure of the program is made to be easy to use. Like, we have these memory values and nodes that are stored in memory, which it seems complex, but it actually is very straightforward to use when you go to do it. So we've got the highest degree node in the locality. There's two different ways we could now go about this. We could say if the degree of next is less than the degree of the agent, we just do nothing. So we say, okay, we're going to say that this is the highest degree node. The problem with this is, in sparse graphs, it's pretty likely we'll end up on some, like, what if we get initialized with on a node that has degree 3 and the next one has degree 1 or something. Like, it all the others are just, or 2, and all the others are just 1 or something like this. Like, we could get stuck pretty easily. So we're going to start with this, and then we're going to work backwards. So otherwise, that's fine. So we've got past that part. So we just want to say agent chosen is 0. So we're no longer chosen. Next chosen is true. And then we can just return 1. And that's all we have to do. So now we have our kernel tag. So I'm going to add this to our header file, and we have this done. So now we just need some way to output at the end what agent ended up being tagged. So we're going to do this in the graph color function, so the main loop of the program basically. And you'll see here we're going to say int tagged node, and then in our print out at the end we can say tagged node %d \n, and then just throw it in there. And in order to get this tag node, we need some way to retrieve it from the whole graph. So we're actually just going to jump into graph util, go all the way down to the bottom this time, and just create a linear search function, because this will serve our purposes for the for this experiment. So find tagged node. We're going to say node pointer graph int num nodes, and then we're just going to insert a for loop on nodes n plus plus, and we're going to say if graph n chosen return graph, and yeah, actually we'll return the not just the ID, we'll return the node itself for you know, future for posterity reasons. It'll be easier to use in the future. So otherwise we're just going to return null, but I'm not going to do any null checks for the sake of the live demo. So now we just need to add this to the graph util.h header so that it's accessible. We can get rid of that, and now we can jump back into our main loop, and we can say find tagged node coloring graph and num nodes, and then we need the degree. All right, so now we can get rid of that, and we just have to add an option to the main function here in order to use it. So we're going to use t for tagged, add a break there, and then we can just say coloring kernel is equal to a function pointer of tag kernel. All right, so now I'm just going to compile. Okay, and then we can just say coloring, and we're going to run it on, do 100, and we'll do 0.5, and then we just need to say -kt. So 62 is the degree of the node. Is that what I'm printing out? It might well be. I might have made a mistake. I did. So it actually managed to identify it, I think, but this should be the ID. So we're going to try that one again. Make clear that, and then we're just going to rerun the command. 73. So you can see this is actually pretty good at recognizing the. So what about higher density nodes then? So 70, it's pretty good. That's pretty good. And then what about really sparse ones? Yeah, so this is what I was talking about with the ability of it to actually. This is really annoying me, this terminal. The ability of it to identify the nodes is going to be more difficult. Well, it's actually doing fine for itself there. So yeah, this is pretty good. I would say, okay, it failed there. So, but it looks like most of the time, oops, that's definitely not right. But yeah, so that's an example of how we can expand the application to kind of do whatever we want it to in a really quick and straightforward way. And that's the end of this demo. So I hope you enjoyed and can see the motivations and how it's implemented. If you want more detail, feel free to read the report and look through the demo. There'll be a link somewhere nearby. Yeah, so that's about it.